Welcome to the second lecture of this course, where we are going to discuss about the atmosphere. The concepts that we would cover in this lecture include the standard atmosphere, an understanding of what we mean by that, the different altitude calculations involving geometric, absolute and geopotential altitudes, temperature distribution in the atmosphere, which includes isothermal and gradient regions of the atmosphere, and we would also like to use the equation of state to obtain pressure and density variation as a function of altitude. What are the key points for the lecture? They include atmospheric vehicles, properties of the atmosphere, the different altitudes, geometric, absolute and geopotential, temperature variation with altitude, the isothermal gradient regions, lapse rate, perfect gas equation of state, pressure and density variation. Let us look at a few important points before we get into some serious calculations about the standard atmosphere. When we talk about aerospace vehicles, they include aircrafts, helicopters, UAVs, balloons which fly in the atmosphere, etc. These vehicles, they fly within the sensible atmosphere and they rely on the air available in Earth's atmosphere for fulfilling their mission. Rockets travel through the Earth's atmosphere after liftoff, and space vehicles like the space shuttle or re-entry capsules, they encounter the Earth's atmosphere when they return from space. If you are sending missions to other planets, the planetary probes, they would encounter atmosphere of a particular planet like Venus, Mars, Jupiter and so on. When you design an aerospace vehicle, you would therefore have to know about the atmosphere. You would like to know about the properties of the atmosphere, and they must be taken into account when you do your design calculations. So, when you talk about a standard atmosphere, what does it mean? What does it provide you? It provides you mean values of important properties of the atmosphere, including temperature, pressure and density, the three most important ones, and they are provided purely as a function of altitude. So, you might be wondering that does it work equally well all around the Earth? Yes, that is the process of standardization, and that adds to the convenience, because it is not location specific. It works equally well across the Earth when we do design calculations. Earth's atmosphere in reality is a dynamic system that we all are aware of. It is continuously evolving through flux exchange and transport. Therefore, at a given altitude over a certain location on the Earth's surface, the properties, they would be dependent on the latitude and longitude of that location, of that place on the Earth, time of the day, that means whether it is morning or it is afternoon or evening or midnight. Temperature is bound to vary, accordingly pressure and density is also going to vary. There are going to be seasonal variations as well as variations due to local weather conditions. So, everything is dynamic, and therefore, it is not very easy to standardize these variations, but that is precisely what is needed, and that is what is achieved through the definition of standard atmosphere. So, how is this standard atmosphere concept developed? It is based on a large amount of data, which is obvious, and those have been acquired from experimental balloons which have been flown in the Earth's atmosphere at different altitudes, and a lot of data has been gathered. And data also has been gathered through sounding rocket experiments. And once these data were available, they were combined suitably to give rise to a mathematical model for representing the average properties of the atmosphere, and purely as a function of height or altitude. So, when you say height or altitude, you would always bring the Earth's surface, the mean sea level, for example, into picture. So, this procedure, what does it do? It standardizes the definition of the properties of the atmosphere, and they could be made available through table of values, and that is what exists, and that is what can be referred by you at any point of time when you are doing a design exercise, for example. This is a glimpse of the temperature variation or the temperature distribution that we see within our atmosphere, and it is shown as a function of altitude in the standard atmosphere sense. So, what you have on the x axis? You have temperature in Kelvin. So, it varies between 160 and 320 degrees or 320 Kelvin. Altitude is given in kilometers, starting from 0, which is the mean sea level, up to around 100 kilometers. That is quite a bit of an altitude anyway. So, you have a zigzag pattern of the temperature, as you can see, through the height of 100 kilometers. So, if you imagine that the temperature on the Earth's surface is about 288.16 Kelvin, then with gain of altitude, when you reach 11 kilometers, the temperature reduces to 216.66 Kelvin. This is a region where the temperature is decreasing linearly. This is defined as the first gradient region. So, we have a gradient of temperature within the atmosphere, and therefore, it is a gradient region. At what rate does the temperature reduce? You would see that it drops by an order of 6.5 Kelvin per kilometer, and it is minus because it is reducing with gain in altitude. So, at that rate, it reduces to about 216.66 Kelvin at 11 kilometer altitude. From 11 to 25, it remains constant. That is what is called as a constant temperature or isothermal region, and that is the first isothermal region that you encounter between 11 and 25 kilometers. Then comes the second gradient region between 25 to 47 kilometers, where the temperature changes to 282.66 Kelvin. It remains constant between 47 to 53 kilometers altitude, then again starts reducing between 53 to 79 kilometers altitude, where it drops to a fairly low temperature of 165.66 Kelvin, remains constant up to 90 kilometers, again increases between 90 and 105 kilometers. At 105 kilometers, it reaches a temperature of about 225.66 Kelvin. So, this is a kind of a zigzag manner in which temperature changes, and it is accompanied by isothermal and gradient regions. So, this gives a first feel of the standard atmosphere, how temperature distribution is standardized in the atmosphere. Let us look at a few different altitude measures. We have named them earlier. So, we said we are going to be interested in defining the geometric, absolute, and the geopotential altitudes. Let us note them down again. Geometric, absolute, and geopotential. These are the words. All of them are altitude measures. Let us draw a simple sketch first. Let us say this is the Earth's surface, this is the radius of Earth, and let us say from the Earth's surface you are at a certain altitude. So, we will define this as the geometric altitude. So, what is the geometric altitude? It is the geometric height above sea level for a point P, which is within the atmosphere. If you say we are interested to know what is the absolute altitude, then absolute altitude is the sum of Hg plus r. Remember, r is the Earth's radius, again in a mean sense. Okay. So, having said that, we are now going to recall about Newton's law of gravitation. We remember about an expression like this: F is equal to G m1 m2 by r square. We are familiar with this expression. So, if you were to evaluate what is the acceleration due to gravity on the Earth's surface, and if you say that that is g naught, you can show that it is inversely proportional to r square. So, that is what it is on the surface of the Earth. If you are interested to know what is the g at an altitude, say h g geometric altitude, then what would that g be? That g be inversely proportional to r plus h g whole square, and this we are concluding from Newton's law of gravitation, the inverse proportionality. Now, if you were to combine these two equations, let us number them one by one. So, we will call this equation 1, this as 2, this as 3, and now we are going to combine 2 and 3 to give the fourth equation, which is the relation between g and g naught, which is given by this equation. This is our fourth equation. We have a couple of equations now, we would need some more actually. So, the next step would be to develop an equation which represents the hydrostatic variation of pressure with altitude. So, as the Hg changes, for example, how does the pressure change from one point in the atmosphere to another where the altitudes are different? So, for that let us draw a small control volume. So, we are drawing a cuboidal control volume. Let this be our axis system x, y, z, and say the positive z direction indicates the direction along which the altitude increases. So, let us say this is the dimension along the respective directions of the control volume. So, what are the forces that are acting on the control volume? If we say that the control volume is fixed, that means a stationary control volume would mean that the forces that are acting on it are in equilibrium. So, there is a pressure say acting on the upper face, there is a pressure which is acting on the lower face. The side forces won't contribute, we will see very soon why. So, there is pressure acting from below. There will be some change in pressure on the upper surface because you have a change in the altitude. and let us say this is the CG through which the weight of the air acts. So, that will be density times volume times acceleration due to gravity. So, the volume will be what? dx dy dHg, that gives you the volume times acceleration due to gravity. Let us say the gravitational force is the gravitational acceleration at this altitude is g. Now, if you write the force balance, then it works out like this: P into dx into dy is P plus dP into the same dx dy of the upper surface plus rho times dx dy dHg into g. Right? This is the force balance. What comes out of it? You get an expression for dP like this. This is our fifth equation. So, it comes from the force balance equation, which keeps the control volume stationary. Now, if we need to find an expression for pressure as a function of the geometric altitude, then in this equation 5 that we just left behind, we have to make sure that we account for the change in g with altitude. That means, g is going to be basically a function of altitude. So, how do we incorporate that change? That is going to be a little difficult if you really want to incorporate it and integrate that expression. So, in order to simplify it, we would assume that the same pressure change would be brought about by assuming that the g is the same as what you have at the sea level. Instead, you will have a different change in height, which is basically fictitious, so that you have the same value of dP produced anyway, which is like saying that you are equating rho g dHg with rho g naught dH, where this change in altitude is a fictitious one. Now, this altitude which we are talking about is basically the geopotential altitude. The only role of this altitude is to bring about this convenience of using a constant value of the acceleration due to gravity, which is available at sea level, instead of accounting for its change with height, because this g is basically a function of hg, and we do not want to go ahead with that complication. So, we have brought in a constant over here. Now, if you equate the two, what do you get? You get a relation like this, that g by, or rather g naught by g into dH dHg is equal to 1. This is the kind of relation you will get. Prior to that, we have left behind an important equation here, which we forgot to number, that is this, where we introduced the concept of geopotential altitude. So, let us call this as 6 and let us call this as 7. So, what have we got now? We have got 3 different altitudes defined, which we set out to do in the beginning. Now, we write that equation 7 like this: dH is g by g naught dHg, and we substitute the expression for g by g naught, which we get from equation 4, into this equation, so that we can rewrite this as r square by r plus hg whole square dHg. Now, we are going to integrate it. When we integrate it, this will be integrated from 0 to h, this will be integrated from 0 to hg, because these are 2 different altitudes we are talking about. One is the geopotential, the other is the geometric. Once you do this integration, what do you get? You get a relation between H and Hg. This is going to be our 8th equation, right. Now, it is obvious that H and Hg are not going to be equal, that is fine, but the good part of it is that this difference between H and Hg is trivially small up to a fairly large altitude. That means, if you are going from the sea level to as high as 65 kilometers altitude, the difference between H and Hg is smaller than 1%. So, for all practical purposes at lower altitudes, they are essentially equivalent. Now, having said that, we are now going to ask the question that how do we go ahead and work out the pressure variation with altitude or density variation with altitude, where now onwards we are going to use H as the height, and keeping in mind that that is not going to be very different from the geometric altitude anyway. So, from practical perspective, using the geometric altitude is always more convenient. While solving equations, we are going to use H. We are going to invoke the equation of state of a perfect gas at this point. So, that is P equal to rho R T. For air, the specific gas constant R is given by 287 joules per kg Kelvin. When we divide the equation 6 by equation 9, we will get a relation like this. So, equation of state once invoked gives us an equation like this, which we will call as equation 10. You can figure out that this can be integrated now to give you a relation for pressure variation with altitude. So, when you integrate this for different layers, either isothermal layer or gradient layer, you are going to get an equation for pressure. So, let us try out with the isothermal layer, that means where the temperature is constant. So, we take an isothermal layer. So, how does it look like? It looks like this. In the temperature sense, it looks like this. Let us say this is the starting of the isothermal layer. Let us say this is at an altitude H1 and you have an intermediate point at altitude H. Temperature, pressure, density all are defined like this: T1, P1, rho 1, etc. And of course, temperature remains constant in this entire layer. Now, in this situation, if you integrate equation 10, you are going to integrate it from P1 to P. G naught is a constant, so are R and T, so they go out of the integral. So, you are going to integrate dH from H1 to H. What does it yield on integration? It yields an equation for pressure. You can get pressure using this relation now for an isothermal layer. This equation, let us number it as 11. Now, from equation of state, if you apply it between the 2 points within the isothermal layer, the starting point and the one at altitude H, how does it work out? The pressure ratio is going to be equal to the density ratio because the temperature is constant. So, you have already worked out the pressure ratio, the density ratio is identical. So, this relation can be called as 12. So, we will keep track of these equations because when we solve problems, we have to invoke these equations. Let us go to the gradient layer. If you choose any gradient layer, you are going to see a temperature change, either reduction or increase. We are looking at a reduction case. Again we start with altitude h1, temperature T1, pressure P1, rho 1, and an intermediate point at an altitude h where temperature is P, pressure, density, etc. The temperature change is linear. So, the temperature variation between these 2 points can be worked out like this. It gives you the temperature gradient, which is called as lapse rate. So, this is called as lapse rate. Let us define this as another equation. This is important for the gradient region. If you invoke equation 10 and then from equation 13 you are seeing that dH is equal to 1 by A dt, where A is the lapse rate, and equation 10 gives you dP by P is minus G naught by RT dH, then putting them together, what do you get? You get dP by P is equal to minus G naught RT 1 by A dt. Now, you integrate it. When you integrate it, you are going to integrate this between P1 to P. You are going to integrate this from T1 to T. Okay. Now, remember that when you integrate, this has to go into the integral. Okay. So, while integrating, this T goes away. Once you integrate, you will get an expression for pressure, which is given by this. Let us name this as equation 14. How would we get the density variation? Let us invoke the equation of state and apply it between those 2 points, keeping in mind that this time, I am sorry, this should be T. This time we have to keep in mind that the temperature is going to be changing, so it will not cancel out. So, what you will be left with is rho T by rho 1 T1. So, that again is equal to this. Therefore, finally, an expression for rho by rho 1, which will be given by this. This is again an important equation. So, now you have equations for pressure variation, density variation, and let us also write down the temperature variation within a gradient region. All that is available to you. That is through the lapse rate. So, now you have the entire mathematical model ready for the standard atmosphere. Okay? So, if you want to solve a quick problem, then it could be like this, that how do you calculate the standard atmosphere values for temperature, pressure, density at a geopotential altitude of say 15 kilometers. So, what would be the approach that you would follow? You would look at the gradient layer from 0 to 11 kilometers. Based on the temperature variation, you work out the lapse rate. So, that will give you minus 6.5 Kelvin per kilometer or minus 0065 Kelvin per meter. Let us assume the sea level values for pressure to be 1.01 into 10 raised to power 5 Newton per meter square, density as 1.23 kg per meter cubed. So, at h equal to 11 kilometers, once you apply the equations for the gradient layer, you will find that the pressure works out to be 2.26 into 10 raised to the power 4 Newton per meter square. Density will work out to be 0.367 kg per meter cube. Now, if you compare these values with the sea level values, you see pressure has dropped to about 22%, density has dropped to about 30% of what you had at sea level at 11 kilometer altitude. Beyond the 11 kilometer altitude, from 11 to 15, you apply the isothermal layer equations, where temperature remains constant, and you will find that the starting point of pressure and density will be those values for 11 kilometers. Based on that, the pressure at 15 kilometers will be this, density at 15 kilometers will be this, and now they have reduced further. This is almost 12% of the sea level value, this is 16%. So, in this manner, you can go step by step covering gradient regions, isothermal regions, and moving to different altitudes, calculating the pressure and density based on the temperature variation that we have already seen in the earlier picture. So, this more or less gives you an idea about calculations involving standard atmosphere. So, you have now got to learn temperature, pressure, density variations in the standard atmosphere. The reference for this lecture would be the Introduction to Flight by J.D. Anderson Jr. Let us conclude. So, in this lecture we studied about the concept of the standard atmosphere. We learnt about the different altitudes, geometric, absolute and geopotential, and their application in standard atmosphere calculations. We looked at temperature distribution within the standard atmosphere, where we saw the different isothermal and gradient regions as a function of altitude. We found that the geometric and geopotential altitudes are almost equivalent at lower altitudes. Application of the equation of state for a perfect gas was demonstrated to obtain pressure and density variation as a function of altitude. So, with this we conclude the second lecture. Thank you.